light this puppy. All right. Now, most of the information that we're talking about today, my folks who are doing the talking in the background, again, if you're not here to review, I don't mind if you leave. It is an option. Also, as spoken before, getting information, hearing it is one great thing, but 9 times out of 10 to retain it, you have to do something with it. That may require you to write something down, draw a picture, something. So just sitting there and staring, some of it will come in, the rest of it will bounce right off the forehead and continue on into space where it sounds like that. So if you have something to write with, go ahead and take it out. If you need something to write with, I have graph paper. Notebook paper, I'm a little off. I don't have so much of, but yeah. Now, again, talking about IMFs and structure of matter a little bit, liquids and solids, and then we'll briefly talk about gases, which is actually where my regs are now. So we can do some straightforward things there. Now, IMFs, a lot of it, again, I'm just going to briefly go over. Forces that occur between molecules. So I'm not looking at the actual covalent bond or ionic bond or metallic bond holding anything together. I'm looking at, I have this substance here, this molecule, somehow, some way that are still attracted to each other. Whether it's a non-polar molecule or a polar molecule, they all have some form of attraction. The key is how strong is that pull. Now, of our types of intermolecular forces, which is our strongest IMF? Hydrogen bonding, wonderful. Now, what do we say hydrogen bonding is going to fall into? Like, how do we get hydrogen bonding? What causes it?
Hydrogen bonding with highly electronegative. Which are like the top of it.
Our big three, NOF, yes. NOF, yes. Hydrogen attached to one of our big three, being attracted to another one of the big three in another molecule. The key here is in another molecule. Now, from there we move into dipole-dipole, which can be any old two polar molecules. They have that attraction because of the what? What would cause a molecule to be polar in the first place?
It has dipole.
Based on what?
A bunch of electrons being on one side and then not on the other side.
Why would the electrons be pulled more to one side in a polar molecule?
Because one of the elements would have a higher electronegative force.
Correct. If I'm dealing with, and I said this is just for a regular polar molecule, I have a difference in electronegativity. One is higher than the other, so it literally pulls the electrons over. Thank you for those who also added in, saying the electrons are pulled more to one side. That is also key. A lot of people make little mistakes by missing out on that fact. All right, last but not least, LDF forces, or London dispersion forces. These, of course, occur with nonpolar molecules. These are also your weakest. Now, if I'm looking at a molecule, can it have multiple types of IMFs?
Yes.
On the same molecule?
Yes.
How is that possible?
It could have like hydrogen bonding and dipole forces because it could have hydrogen bonding on one side and then one side would be really like have high electronegative and then has a dipole moment makes it a dipole. Yeah.
Okay. So if I'm taking a look at, and I feel like this is probably going to knock me off for a quick second, so I can write on screen. Of course it will. There we go. So if I'm taking a look at the molecule here, C, just because I need the clearance. Really? This doesn't like me. And it erased it. Thank you. All right. Let's try it one more time. If it doesn't work this time, I give up. I'll write it on the actual board. Well, I'd like for those who are not here to be able to at least venture back to see what I'm talking about rather than random words. C, O, oops, that's not a double bond. Nobody saw that. That one doesn't exist. Doesn't exist. You didn't see it. Now, of course, on each of our other carbons, let me get rid of that because that doesn't exist there either. These are hydrogens. We have a lot of stuff that's invisible. Stop. It's okay. All right, now, if I'm taking a look at this molecule overall, identify where based on what you did see on the screen, where would I have my polar side of the molecule then?
On the right.
On the right. On the side that was closest to our oxygens. That's correct. There we go. Yeah, it stayed. Okay, so if I'm looking at it, where my oxygens are, it doesn't change the fact that it's still highly electronegative. So these aren't just going to pull electrons from this carbon. They're pulling electrons from the entire molecule. The closer the atoms are to these oxygen, the more they're going to pull, okay? So don't think of, oh, it's only the one it's connected to and there's a wall surrounding it so it doesn't interact with anything else. If it's highly electronegative, it's pulling from everywhere that it can. Now, if this end of the molecule is more polar, where would I have my LDF?
On the left.
On the left part of this molecule, that's correct. Now, question, what type of IMF would I have surrounding this oxygen here?
Hydrogen bonding.
Hydrogen bonding, how do you know?
Because oxygen, hydrogen bonded A3. Hydrogen bonding.
Appreciate that. You're okay, Dominic, you're okay. All right. Yes, I would experience hydrogen bonding here because this, not only does this make it polar, but oxygen is one of our big three, and it's pulling the electron this direction, which is making it slightly negative, meaning a hydrogen has the ability to attack from that angle. Also remembering, oops, I'm trying to draw on the laptop. Also remembering that this hydrogen here would actually be more at an angle because of the fact that we have our two lone pairs that will also be there on here. Dot, 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 dot. It doesn't want to show up, but you know what I'm talking about. All right. Now, always remember, these are much weaker than covalent ionic bonds. Again, it scared me when I heard people tell me that ionic bonds were weaker than hydrogen bonds. It's a completely different spectrum, okay? Ionic, covalent, intra, inside. If I have hydrogen bonding, dipole, London dispersion, inter, between. So it's outside, but between two molecules. Given the example here, again, just explaining what's happening, giving you water as, of course, the ultimate example. When things go south on you, and you're trying to figure out which one it is, if it's dealing with hydrogen bonding, I picture water regardless. It makes it easier for me to say, okay, I know how this is going to react. I know this is going to respond this way. The hydrogen is slightly positive. The oxygen is going to be twice as slightly negative. And then I arrange things based on that. As you saw on your original mock, there was actually a situation where they gave you 4 molecules and asked which was the example of hydrogen bonding. I had people tell me that this was hydrogen bonding. There was one example where it had hydrogen to hydrogen. There were people who told me that was hydrogen bonding. No, it is just hydrogen attracted to a highly electronegative on another atom. So that's NOF again, NOF, nitrogen, oxygen, and fluorine. Now, when we deal with phase changes, remember we're not changing the substance itself. If I boil the water inside this container, it looks like it's boiling now, but it's just carbonated. If I boil it, it's still water. All I did is change the state. If all I do is change the state, all my forces, all my bonds are still there. Biggest thing I have to overcome is going to be the attractions between. What makes London dispersion forces strong? What kind of situation do I want to look at if I want strong London dispersion forces? There are 2 types of situations. Park, can you give me one?
Random electron.
That's what causes them. So that was actually another question I could have asked. But what type of situation am I going to look at where I know this is going to have stronger London dispersion forces?
Like the bigger molecule.
Bigger molecule or it kind of goes along with it. Virginia? I'm putting that in with what Rhea said about the larger molecules, because I have a bunch of larger molecules that will cause it. But what on those larger molecules would cause, it ties to what Parker said. The larger the molecule or atom, what does it have more of? Electrons. If it has more electrons, more random electron movement, which is going to increase the strength of your London dispersion forces. This is why when we did our marble drop test, not marble, pond stone, whatever you want to call it, our mineral oil, our glycerol, and our, I think it was water, the stronger the forces between, the mineral oil had stronger IMFs, even though it's a nonpolar molecule, because of the interaction of the London dispersion forces and the size of the molecule. Now, this is tying this concept that we just talked about in Big Idea 5 to Big Idea 2. How do you think the IMFs are going to affect entropy?
I would say the stronger the force, the smaller the amount of entropy there is.
Why?
Because since the force is stronger, it's holding together the molecules like tighter together, so there would be less entropy, being that entropy like this over.
Okay. What about the boiling point? How are IMFs going to affect the boiling point? Why? Correct. Notice that this question testing the same exact knowledge, but it's written in two different ways. Okay? So, if we're looking at entropy, because of course we know that AP loves to mix concepts, they don't want to just say, what is an IMF? And give you a definition. Instead, they're going to say, same concept, let's write it two different ways and see what they say. Let's see what they do. So, both of these come down to the more, it's going to be harder to have a high entropy if there's strong attraction between the molecules. It's going to be harder to increase the entropy enough to get to the boiling point where they can escape the liquid phase and get to the gas phase if I have stronger interaction between them. Therefore, the boiling point, higher, the stronger the forces, the higher the boiling point. Ta-da, words. Basically what we just said. Yeah, and this is really just explaining the distance between the two. Just explaining the difference between them. Solid to liquid, you don't have to disrupt the characteristics all that much, just enough for them to be able to move past each other, get them a little bit out of order, the order that they had as a solid, but getting it to a gas phase, I have to get them completely separated, far apart, moving fast, high energy. Issues, questions, concerns? Wonderful. I thought I deleted that. Basically pointing out that the dipole moments that we're talking about are just the electrostatic attractions between the slightly positive and slightly negative ends. Now, question. That answer's too easy. Why don't all slightly positive atoms in a polar bond respond the same way as hydrogen does?
Because hydrogen only has one electron.
What does that mean? What does that mean? Nathan got you started. He said hydrogen only has one electron.
Does it all have what rule?
True.
I'm saying it's already in a bond. But I'm saying, why is it that if I were to have, I don't know, chlorine with oxygen, it doesn't behave as strongly as hydrogen would attach to oxygen? Nathan got us on the starting path. Who do I want to call on since people got silent on me?
you say
Can you say your question one more time?
question again?
The question is, why is it that if I were to have, and I'll use the exact example, if I were to have OCl2 versus H2O, why is it that the strength of the slightly positive end of hydrogen will be that much stronger than it would be if I'm dealing with OCl2?
Is it because hydrogen has a only one shell, so it tries to pull the electrons closer to it?
Well, we've already established that the oxygen is pulling the single electron away. So what's left? Somebody. Okay. You guys are deferring to each other, so I'll go to the middle. Here you go.
The difference in electronegativity, the differences.
Should I use nitrogen? That way, for nitrogen and chlorine, it's about 3.0. Okay? But no, that wouldn't give me what I want because I need a difference of about 0.5. Why is it that OCl2 is less polar than H2O? Other than the whole shielding thing. You can keep going.
Just like Cl has more electrons, right? So they have more shielding, and then like when it bonds with oxygen, it's gonna have like less bonds because Cl has a stronger nuclear charge than that of hydrogen, and then because there's more electrons in chlorine, we should have more repulsion.
You're like right here. All I'm waiting for you to do is just cross right over the line.
Okay, and it's like
Okay, so far, if I can sum up with what Rajiv has said. Rajiv said, when we deal with chlorine, more electrons, even along with the fact that it has a stronger nuclear charge, so the more electrons are going to create more repulsion, right? Right? I'm making sure I'm saying what you said. Okay. Versus hydrogen, I pull the electron away, what's left? What's the only thing left with hydrogen?
A proton.
A proton, the nucleus. That's where the protons are. That's the protons. Now, if I'm dealing with something like hydrogen, because they ask questions, they won't ask them, of course, like that, but they'll ask similar questions along that line. Why is, or this has this strength of a dipole moment. This has this. Explain. And a lot of times it goes back to what we talked about on Tuesday and the day before, before the break. How are the electrons arranged? What does that mean in terms of our periodic rings? How is that all going to work for us? Okay? So everything is interrelated. Do not try to throw something out and be like, they won't ask about that. We talked about that. Talked about that.
Wait, can I copy that down? Or just take a picture?
This is also going to be posted via YouTube if you want it, or you can take a picture. That's fine. I looked at my phone after Philadelphia, and I have an entire PowerPoint, and then they said, I'll just send it to you. So just if you want me to email it to you, I can do that. All right. Melting points, boiling points. We've already said this this concept. There we go. The higher the IMFs, or stronger the IMFs, the higher the boiling point. And this is a graphic representation. Question for Rhea. Why do we notice the trend that after the first period, we drop significantly for all of them in terms of our boiling point? All of these are with hydrogen, hydrogenated, words. They don't want to work. Hydrides with a specific element. After period 1, we drop significantly except for carbon. Why do we see this trend? Those are the big,
The hydrogen
chlorine, and then there's ammonia, and there's H2O. And they're all hydrogen bonded with the same. So they have the strongest intermolecular forces. They have hydrogen.
Okay, based on what else in their structure?
Should I tag team them?
You tag team with Bree? Oh, thank you.
I am not doing
Go ahead.
Ah.
Think about structure. Hold on. What did I just say before I asked that question? Everything is interrelated and it all goes back to structure. What about the structure of these three is different when you get to that third period? Because remember, these are all in the second period. These are third period. What's the difference?
Oh. Wait, are you saying why it's like so much?
Why we have such a big drop in boiling point from here, then down to here? You pass? Who else has been quiet today? Race.
Wait,
I can't even see it.
Well,
Mr. Baldwin,
Yes.
CH, whatever the subscript is.
CH4?
It significantly raises the nuclear victory.
That's the only one that doesn't follow it. But again, the question is, what about the structure of these three, nitrogen, fluorine, and oxygen, would cause you to have such a significant drop afterwards when we go down one group?
it's because of their large ionization or ionization energy or no electronegativity. It's more electronegativity, so it pulls hydrogen closer than the rest of them, so that makes it harder to separate.
What also, along with having a high electronegativity, because that's what each person is giving me, what else would be conducive, using those big words, not really big words, but nice words, that would allow for that attraction to happen? What else in their structure? What else in their structure would allow? Hint, it's another periodic trend. Say that again. What about the atomic radius of these three? What about the atomic radius of these three would do that?
It's a smaller radius, so that means that the electrons can get closer to the protons and have that larger pool.
Correct. If I'm looking at these three compared to the others, these are where I'm also dealing with some of my smaller atomic radii. My noble gases, they have smaller radii, but they don't bond, so can't really do anything with that. But for nitrogen, fluorine, and oxygen, they have very, very small radius, or radii, which means the electrons from the hydrogen can be pulled in even closer, which is going to give a higher electronegativity, give them the ability to have more of that effect, which is then going to raise the boiling point. Now, there was one other thing I was going to do, but I'll save that one. I'll save that one for another day. Now, the graph kind of alludes to it, but we'll save that for another day. So think about, if that's the case, we would expect that fluorine would have a smaller radius than oxygen, but water has a higher boiling point. That's a whole nother story for another day.
Oh, the mystery.
Ooh. All right. Now, which of the following is capable of forming stronger IMFs? That should be like a... How do you know?
Because of then two is the same.
No, not because of hydrogen bonding. Guys,
Oh, because look.
what about water itself? I think that's where we make the mistake. What about water itself would give it a better suited IMFs? Not hydrogen bonding. That's saying, okay, we have the between the molecules. Richard is like, please let me answer. But
Is it because it has a smaller
We did it again.
it's a smaller
It's simpler than that.
That's how transfer occurs.
It's simpler than that.
Let me enlighten you guys.
Tomorrow.
Okay. It's HO because there is more, like, there are two different elements instead of just one.
And if I have the same element,
If you have the same element,
I have the same what value?
yeah.
I have the same electronegativity value. If it's 1 minus 1, I get, which would make it nonpolar, which means London dispersion. Okay, now, notice, tripping point on this question. Tripping point on this question. Which molecule is capable of having this? It goes back to the structure, not just looking at it and saying hydrogen bonding. I know this one is going to experience hydrogen bonding, but why? That's what we're trying to figure out. If I look at the structure of the molecule, if I look at the properties of how those elements come together, what in that setup tells me it's going to have the stronger IMFs? We'll save this one because we're going to do this part later. Now, here we go. Which gas would behave more ideally at conditions of pressure and temperature? At the same conditions of pressure and temperature. What does it mean when we say ideally? What is stable?
It's that constant.
We just watched the video on it.
118.
Oh. I thought you had your hand up. And he's looking. I thought your hand was up like, I'll give it a shot. Okay, now before we started talking about the KMT. Those 5 statements, he took it into 5. Really, it's 4 statements about how gases behave. We want to say that they collide elastically. Meaning, same energy they came in with, they leave with. There's no stopping, there's no nothing, it's just, there we go. No attraction, no extras. That would be ideally. If I'm looking at it between these two, which is more likely to be polar? Which molecule is more likely to be polar? CO, why? 2 elements. 2 separate elements, 2 different electronegativities. Versus nitrogen, same element, completely nonpolar, which means between these 2, they're most likely to bounce off each other without being attracted. If it asks which one would behave more ideally or more like a real gas or something like that, what it's asking you to do is look at the structures, look at the polarity of the molecules, and determine which one is going to basically act like it doesn't want to be in contact. Which one is going to act like it's in a perfect situation? No attraction, no real transfer of energy, that type of situation. Yeah. We know the basics of how liquids work. If I were to take this, do you trust me, Robert? You trust me? Okay. If I were to take this and say, nothing's going to happen, why? There's a cap on it. So what am I essentially trying to do at this point? I'm trying to make some type of liquid compress. That's not going to happen. Why? The particles are too close together. Don't worry, next year we'll have fun. Now, if we're still dealing with IMFs, the next thing that we're going to have to figure out is how they behave even as a liquid. Will they have a high surface tension or high viscosity? Low viscosity. All this goes back to IMFs. So, liquids, larger IMFs tend to have high surface tensions. So, water striders walk on water because the molecules are stuck together enough where it happens. Yes, sir. I can take this, and if done at the right pressure, notice it ran right down, but it grouped together. I can shake it, It's not really going anywhere. Why? The cohesive forces
Are stronger than the adhesive.
the cohesive forces are stronger than the adhesive forces. It's more important for them to stick together than to try to stick to whatever it is they're on. Now, capillary action, I haven't seen in the past couple of years where they've used it a lot, but just understanding how viscosity works will be your best bet. Stronger IMFs, higher viscosity, lower, weaker IMFs, lower viscosity. Go back where? This is saying the same thing as what's on the next slide. The other thing just does it with a picture. One more. This one? Good? What? Cohesive and adhesive? Yes. For what we just did? Yes. For water? Yes. Same thing for mercury, which is what you're seeing here. If you're looking at something that has stronger adhesive forces, you would expect that it's going to stick to stuff. Adhesive, like glue, tape, are adhesives, so they stick to other things. Cohesive, sticking together. If I'm looking at mercury here, it does not want to interact with my glass. It would rather stick together. So those cohesive forces create a convex meniscus, whereas
Which force dominates?
which one dominates you? Ha ha ha. No. All right. Now, we're seeing the opposite when we deal with water. It's almost like it's trying to climb out. Stop. If I'm looking at here, for adhesive forces, having a concave, it's almost like it's trying to climb out of a cave. That's an easy way to remember. Convex, staying in. Concave, it's trying to climb out, like trying to climb out of a cave.
I'm standing on a cave. Or like a volcano.
We just talked about this. Types of solids, and we'll breeze through this part quickly. What time do we have? 3:15. So we're about at just the perfect spot. All right. Now, if I'm looking at solids, of course, not all solids behave the same way. We have amorphous solids like rubbers, like glass, where they don't really have a set structure to them. And then we have crystalline solid. Everything is ordered, and we have what are called unit cells. Now, when we deal with crystalline solids, these are the three main ones that we talk about. Ionic solids, which we said we'll get into more with lattice energy next time. Molecular solids, discretely covalently bonded. Notice it says for molecular solids, covalently bonded. And atomic solids, where the actual lattice points are atoms in that structure. Given examples, diamond would be more of an atomic solid. Notice how at each point we have the covalent bonds that are streaming from each of these individual atoms. For the ionic, it creates this lattice structure. Of course, we know we don't have a full bond there. We have just attractions. And Coulomb's law plays a big role. And last but not least, a molecular solid with water. The interactions between them are more along the lines of our IMFs. Yeah, I'll post this to Moodle, and if anybody wants it, I'll email this PowerPoint out, because I know you can't see that. But it just basically says the same thing that I said a second ago. So I'll put it on Moodle, and if you want it, let me know and give me your email address so I can send it out. This PowerPoint. The video will be on YouTube. If you want just the PowerPoint to look back at, like the tables and stuff, I'll put it there. All right. When we talk about metallic bonding, and after, at least, not after, during this part, I'm going to point you to another video of something you want to look at for semiconductors. That's something that they've added in a little bit more in the last couple of years. There's a video by Veritasium. It's very, very good. That's the YouTube channel name, Veritasium. And it goes very, very detailed, but very comprehensible material for It is very comprehensible material for semiconductors. Now, when we look at metallic bonding overall, we look at it according to this model, electron C model. Basically, I have a bunch of cations. The electrons are delocalized. Delocalized meaning what? Delocalized. They're free to move all over the place. They're not stuck to one specific atom. The localized electron theory, which is what we use for our Lewis structures, means that they're stuck, quote unquote, on that atom. In real life, it doesn't really work like that. They're free to move about. Same thing happens here.
Could you say that they are far out?
What do you mean far out? I figured you were going to a 70s reference there. All right, now, the stronger the attraction of the cations in the center, probably the closer they're going to hang together. We don't talk about this one much. Substitutional versus interstitial. We brought this up a little bit on Tuesday, and I think there's a diagram. There we go. If I'm dealing with a substitutional, it is the atoms are about the same size, and it is just like having a substitute teacher. Something is put in place of. If I'm looking at an interstitial, inter, again, hearing that prefix, you should be able to say, that stem, you should be able to say inter, between. So interstitial, I have other atoms, usually much smaller, in between in the gaps of the particular alloy, or the typical metal.
Wait, what? Oh, so they're just put in.
So it's literally like stuffed in between here versus this. It was almost like pulled out and another one substituted in place.
So the alloy is stuffed in, or?
The other metal, which makes it an alloy, is what's stuffed in.
Okay.
Now, the whole point again for alloys, some metals are not as strong, more flexible. This means that it's not as easy for it to hold up to the purpose that it's set up. If you have, say, a gold necklace or a gold ring, watch, whatever the case, okay. The number of carats is also letting you know a little bit about the purities, but also some of the other things that are mixed in to make it more durable. Gold is actually relatively soft, not extremely soft like sodium, but it's relatively soft. Copper, very, very soft metal. Iron rusts, but also it can have some certain characteristics that will make it a little bit softer. By adding in some of the properties of carbon, makes it more durable, it can withstand more heat, and so forth. Network solids, this was another one. I had people tell me that is actually held together by hydrogen bonding. Why would that not be held together by hydrogen bonding? There's no hydrogen. To go even further, there's no hydrogen at all. If I'm looking at this is graphite. Graphite is just another allotrope of carbon. It's all carbon bonded to each other. The attractions are going to be purely London dispersion. Why would this one not have hydrogen bonding?
Because it's a diamond and it's made up of carbon.
Okay. Again, the same answer. It's one, there's no hydrogen, but two, what else would disqualify this one from having hydrogen bonding? What are these bonds? Those are covalent bonds. Those are not attractions between molecules. Those are actual bonds. So, you can't have hydrogen bonding if I don't have two separate molecules to work from. This is going to it. So we'll talk about this with bonding stuff. What you're seeing here, these are actually what type of, are those sigma or pi?
Those are sigma, apparently.
Ooh. I knew you were going to say those. Notice they're sticking up, above and below, above and below.
What? What ones are like this?
This is the plane. The straight lines and the dashed ones are the plane. The balloons are above and below the plane.
Oh, so that's
Huh? Pi bonds are always single, yes.
but a
Oh, no. Sorry, sigma bonds are always single. Woo, you almost made me say something wrong. I don't like that. Single sigma. Single sigma. Sigma single.
Wait, what?
Oh,
Wait, no, but I thought a pi bond always has a sigma bond in it.
It does. A pi bond always has a single bond in it, a sigma bond.
A signal or a sigma?
Sigma, which is going to be a single. But all single bonds, if I just have a single bond, it's a sigma. Now, who was it? Somebody over the, when we were back in Big Idea 2, they came up with a way to do it. They just looked at the board and it made sense. I had carbon, carbon. We have the overlapping here, and then we have our available p orbitals. This was the sigma. This one here, if anything was happening, this was pi. These electrons are being shared above the plane. They noted that there's a line here, there's a line here. If I turn the board, we were using the smaller board so it was easy to do. They turned the board and noticed that, hey, two lines looks like pi. The actual Greek symbol, pi.
Wow. That's so crazy.
First one was sigma, then pi bond, okay? They were able to turn the board, sorry.
Wait, so sigma bonds are on the plane?
Sigma bonds are on the plane.
Wait, but in a pi bond, where would the sigma bond be? Would it be?
Still on the plane. Notice for each of these, the carbon-carbon bond is still here.
Yeah.
But after that, then I'm going to have some attraction that's going to happen here.
But then what?
That could happen there, I'll say.
Okay.
If electrons are being shared, it's going to happen above the plane between these two p orbitals. It's not going to happen anywhere else.
So then there's two sigma bonds in this thing.
No, there's a sigma and a pi.
Okay, but then wait,
If I have a triple bond, then I have a sigma and two pi bonds.
okay, but if a question asks you how many sigma bonds are in this thing right here,
Usually they're going to ask you that about a molecule. And that's actually a very good question. Because the mistake that a lot of people made, see, this is bringing back a lot of those questions and things that kept running through my mind. People would make the mistake because for organic, they write it in a condensed formula, and so they may write this. Of course, there's more stuff here. And people forget to count the sigma bonds that are here between carbon and hydrogen, and there are 3 bonds there. If I have a couple of those spread out over the thing, I'm going to be missing some bonds, and my answer will be horribly wrong. So it may ask how many sigma bonds are in this compound, how many pi bonds, those types of things. How do you know? What's the shape? What's the shape around this specific atom? Now, ceramics. Usually ceramics and our ceramics, we know those. How many artsy people do we have here? Enjoyed 3D art with, she's there, she's a lady, she's Miss Davis. When you're making ceramic, why do they use ceramic? It can tolerate very, very high heat. And it's also many times, I think, more of a amorphous solid as well. That's what gives you the ability to sort of change it. It's not changing it into glass, it's changing it into something gas-like. Huh? I don't know.
It looks like somebody did it.
Somebody may have. I don't know.
You can't buy the penny.
I was going to say, you pick it up and it works. All right, now, to wrap this up, what I want you to do, because really that was, we only had a couple little things on there, so we'll finish that up next time. We're going to talk about, technically it fits into network solids, talking about semiconductors. The guy's name, you want to go and see his page, V-E-R-I. Let me look it up. It might be an I, it might be an A. Does anybody in here watch videos on Veritasium? No? Oh my goodness, you guys are missing some stuff. You guys are missing. Good Mythical Morning is kind of interesting. They have some nice stuff and they have some dumb stuff.
I don't like it when they do the bullet something.
There's only so many times you can do that. I spelled that horribly wrong.
They always do like
Here we go. Veritasium. Now, this guy, a lot of his stuff is more along the side of physics, but he has where it connects with chemistry very, very well.
Wait.
For those who didn't know what I was talking about searching on the page, notice home, videos, playlists, blah, blah, blah. Search. Semiconductors. There we go. Huh? No, you can do that on Windows. No. Go to the page. You have to go to the person's actual page. And then it's right there in the toolbar. They've had it on there for almost a year now.
Oh.
For over a year now. Sorry. So, the name of the video, and this is, again, in understanding how semiconductors work, is his video is called How Does a Transistor Work? For the laser photonics people and electronics and stuff like that, this will also help you to get a better understanding of how things are arranged and so forth. Huh? It's 8 minutes. 6 minutes. 6 minutes. All right. So at this point, I'm actually going to stop things.